Good morning, everyone. I am Mr. Ish. Thank you for watching. Thank you for liking. We are doing here a derivative word problem video. We will look at a single word problem. It's a derivative rate of change word problem. Slightly difficult. And here it is. We have a specific wooden plank that's leaning and resting against a wall. Everything here is with regards to the floor. Everything is resting on that. This 10-foot wooden plank leans against the wall at a certain angle. But the floor is rather slippery, so the wooden plank starts to slip, and it slips in the direction, as you see, at a rate of 2 feet per second. You know, as the wooden plank is slipping, it's going to fall down in terms of height. We have a movement over here, and then from the top edge right here, it's going to start slipping down until it finally falls flat on that floor. But you have a certain angle here created by the wooden plank against the wall, and you know, as this wooden plank is slipping towards the right, this angle is going to get larger and larger. We have to find the rate at which that angle gets larger. Right here being our question, we have to find the change in that angle over change in time, given what we know. We're going to do this in a methodical manner. I'll show you the variety of steps involved. This is slightly a difficult question, and we have all of this before us. This 10-foot wooden plank right here, from here to here, is 10 feet. And it is lower edge right here is 6 feet away from the wall. We have all of that. We don't have the angle, we don't have this, but we easily can determine that. It's not hard. We have a slipping rate here at a rate of 2 feet per second. So let's start working on this problem. By means of the wooden plank against that wall at a certain angle, we're also creating a right triangle. Let this side be x, let this side be y, and this z as we had originally determined it to be the case. We can easily find y. It's one of those Pythagorean ratios. 8, 6, and 10 will easily give you that. We have here y being 8 feet. We know that. We have x over here being 6 feet. Let's determine that angle because we need that angle. Theta over here, you can do it very well with regards to x and y because these are the things that are going to change. Let's do the determination of the angle. Tan theta is equal to x over y. With regards to this theta, this is opposite, that's adjacent. And you know, tan theta here is equal to 6 over 8, and theta is equal to arc tan 6 over 8, which is 0.75, and we'll save that value. We don't need to really calculate it for right now. We have that value determined, and we're going to save it. Now what we need to do is find a couple of rates of change. We know the rate of change of this x, which is the slip, is 2 feet per second. It's a positive value because as it's slipping, the wooden plank is slipping, this x dimension or distance from the wall to that lower edge of that wooden plank is getting larger, so it has to be positive. We have to find the rate of drop of this dimension in terms of y, because as it slips, this height falls. We have to find the change in y and the change in time first. So how can we do that? Use the Pythagorean given what you know. You know x squared plus y squared here equals z squared. If you were to apply the rate of change of all of this, you will have the rate of change of x over time, x squared. You'd have the rate of change of y over time, y squared, and then you'd have the rate of change of the z dimension over time, z squared, and these are easy to derive. The derivatives of each of these are 2x dx over t, and then here you have 2y dy over dt, and then here you have 2z dz over dt, and we have these values of x and y. A good point to remember here is as this slip occurs and this wooden plank drops down, nothing will affect the z dimension. The wooden plank will always stay 10 no matter what. The wooden plank stays, or this hypotenuse will always stay 10. This x value will get larger, the y value will get smaller, but the z value will stay the same. The rate of change of z here is always equal to 0, therefore all of this zeroes out, and you must understand that fact to proceed. So all of this zeroes out. We'll put in our missing values here. We have a 2, we have an x dimension here of a 6, we have a rate of change of the x is 2 feet per second, plus we have a times 2, we have a y value here of 8, and we're calculating this rate of change of y, and this rate of change must be negative because this y dimension will get small with time. Here we have a 16 dy over dt is equal to 2 times 2 is 4 times 6, 24, and then rate of change of dy over dt is, this right here is a minus 24. When on the other side became a minus 24. Minus 24 divided by 16, which is a minus 1.5 feet per second. That's the rate at which this y dimension or this y length is getting smaller. So we have to save this value and we'll put it right here. The rate of change of the y dimension is minus 1.5 feet per second. So we have determined a bunch of useful items. We have this, we have that, we have the x, we have the y dimensions. Now what we need to do is actually determine this, and we will do so, and it won't be hard. Now to find the change of the angle with respect to time, because as the wooden plank slips away, this x dimension gets larger, the y dimension gets smaller, but the theta angle will get larger and larger. It's going to become larger up to a certain point. Once the wooden plank falls all over on the floor, this right triangle representation is all gone and none of this would apply. But so long as the wooden plank is still leaning against the wall, we have a change in that angle. What equation will allow us to do that? How about this? Tan theta, again, it represents the opposite over the adjacent, and you would do the rate of change determination of this. The change in the angle or the change in time, tan theta, is equal to the change of these x and the y values, but here the x and the y values are in terms of a quotient, and you have to bring in the quotient rule of derivatives, and you know you're going to bring in that. You'll have your f function, your g function, and bring in the quotient rule y times the change in the x, change in time of x minus x variable times the change in y over the change in time of the y variable all over y square. Now let's do the derivative of tan theta. You know it to be a secant squared theta, and you still are calculating for this change in the angle or change in theta or change in time. We're still calculating that. Now let's do this. The derivative of x and y in all instances is just a 1 and they go away, because you're just basically looking at a derivative of something like this, where by the power rule it becomes 1x to the power of 0, which becomes 1, and the same applies to that y. All of that quotient rule expression easily simplifies to this: y dx over dt minus x dy over dt all over y square. And here what we can do is easily put in the numbers. We know the y value is right here, 8. So let's remove this and put it in 8. We know the change in x over change in time is right over here, 2 feet per second, because it's slipping and becoming larger with time. And this right here is a 2. So let's bring in that 2. We know the x dimension here was 6 feet. Originally it was 6 feet here from the wall to its bottom edge. It was 6. So let's bring in that. We know the change in y over change in time. We've calculated that. It's right here, minus 1.5 feet per second. We know the y dimension, it's 8. 8 squared is 64. So we have all of this. When we do this calculation, we need a calculator. We can do 8 times 2, 16, plus 6 times 1.5, all with the minuses cancelling out, plus 9, and divided by 64, I get a 0.309625, which I will very well bring right over here. 0.390625. What I need to do is calculate for this change in angle over change in time. I would take this secant square value on the other side, but when I take it on the other side, I'm going to actually apply it with regards to the theta. We know theta is equal to all of this, so I'm doing secant square of arc tan 0.75, and then we have that value to be determined, and it's not hard, and that right there will give you exactly what you're looking for, which is a change in this angle over change in time. We have 0.390625 divided by this value right here, which you can do everything here on the calculator. Put 0.75 inverse tan, you're doing the arc tan, you get 36.86 degrees, and then you cosine it, because I can work with the cosine and make it reciprocal. I do a cosine, I square that because I have to get that square effect, then I make the reciprocal of this value, I get a 1.5625. So all of this value in terms of its numerical output is 1.5625. All that remains is a simple computation right here, which I'm bringing right over here, and let's do it. We have a 0.390625 divided by 1.5625, and that right there is a 0.25. But what does this 0.25 mean? It means 0.25 radians or rads per second is the change in this angle, and it's a positive value, which means as a wooden plank slips away from the wall and it goes towards the right, everything drops down. This angle will get larger in terms of a positive value here of 0.25 radians per second. The angle theta will get larger by 0.25 radians per second, and our answer has been done. The question is completed and the derivative word problem is successful. And with that, I tell you, these derivative word problems are usually rate of change problems, and you start with an equation and you somehow determine what you have and what you need to find out, and you apply the rate of change aspect to it to take it through to completion. Thank you for watching. Have a nice day.